of things that we should do.
Nice.
Oh,
What do you do in the shower?
I
shower
think of
thoughts.
math. I think about math in the shower. Okay, wait. By the way, wait. So did you guys manage to do this?
No.
Isn't
No
that
one did it.
basically just
Why did
stating
nobody
the
do it? I was
theorem?
okay.
I mean,
oh my God.
it's way out of scope.
Okay, sure. I mean, this is just a little
Not-
little fun thing. Little fun thing. It's all good.
Wait, what do you mean by less than less than?
Oh yes, the definition is up here. So you have two functions. We have that f is less than g when g is eventually bigger than f. This is eventually bigger, meaning that there's a certain point which after that point f is
Okay.
always less than g. This is
Okay,
not the
yeah, sounds
definition
good.
that they use in 137. But yes,
Or 236?
137. Because
Oh,
this
it is the
from
137 definition?
This is from 137, yeah. Or
Okay.
supposed to be from 137. And then I fucked up the definition, but it's okay. So, anyways. So, in order to understand master theorem, you need to understand how to manipulate the definition. Am I recording? Okay, you need to understand how to manipulate the definition of the big O of bullshit, okay? So,
Mhm.
I'm going to recap the definitions for anybody that missed it. So, we
Basically
have...
everyone.
Hmm?
So basically everyone, because
Yeah.
there was only me there.
Yes. So you have g of n is a function, and f of n is also a function. Okay, and then we say that f of n is O of g of n. This is if and only if. So it's an equivalent definition. This means that there exists a c greater than 0 and an n not greater than 0. So that for every, not x, for every n greater than n naught. Wait, let's do this. Remember this guy? This greater than that implies that okay.
Wait, does it have to be absolute value? Because they never put that.
The formal definition is absolute value, yes.
Oh, we've been missing that. Okay.
Yeah, so funny thing is, funny. Here's something really funny. Okay. So this n is actually O of negative e to the n.
And
Yeah, it's kind of funky, but this is true. But conventionally, this makes like 0 sense, right? So nobody, like, it makes no sense to do practically. So you just don't. You just define it as like positive functions.
I see.
So yeah, so that's for that's for the big O. Let's talk about the big omega. So this one is actually just the exact opposite of big O. So you still have a C. I'm going to call it D. Actually, we'll flip it. So this one we'll call D. And this one we'll call C. Alright. And we'll use the same n naught here. Well, not the same one, but we'll just use the same variable. And then you see this quantifier here, the for all n in natural. That one is optional most of the time. So you don't need to include it in the actual statement. It's just kind of implied when you say that n is greater than n naught. And it's the exact opposite, so instead of a less than, you get a greater than, equal to. That. Okay. So the difference is, instead of finding an upper bound for your f of n, you have a lower bound for your f of n. And you might be thinking, in terms of program runtime, why does it matter to find a lower bound? Well, it's important because when you're trying to find your tight asymptotic bound, which is also known as your big theta of g of n, this means, so instead of one constant like c or one constant d, you have two constants c and d. Isn't that crazy? CD's nuts, by the way. Alright.
Oh.
So, and I'll just continue writing the definition. So, this guy is a tight asymptotic bound, which means that this g of n is actually a lower bound and an upper bound for your f of n. So, you have g of n at the back hitting you from behind, and at the same time, you got another g of n hitting you from the front, bro.
There's no escape.
Exactly,
You're
bro.
gonna-
One in the ass, one in the mouth. It's like
It's
a Eiffel
from both
Tower.
sides.
Exactly.
This is
There's no
being
escape.
recorded. It's official one that's gonna be uploaded on YouTube. Please
Yeah.
keep it.
Exactly. I'm gonna upload this to
PG?
YouTube. Wait, that's actually that's a good idea. I'll do that.
Yeah.
Exactly.
Will the
see?
commentary be included?
Of course.
Yes.
That's the point.
Of course.
It'll be monetized.
Okay.
Will it have ads?
I'm probably not gonna give ads, but yeah.
It automatically adds ads.
I think I can disable them. Okay. Anyways,
Can you?
yeah. So, here's a short theorem that I wanted to keep as an exercise, but I realized that it was kind of too easy. So, all right. So, example. So if you have two functions, so if you have two functions f and g, if f of n is O of g of n, and f of n is also in omega of g of n, then f of n has a tight asymptotic bound, which is the same as g of n. Okay, now this one should be pretty quick to prove. Like, let me just show you. Because it kind of just like follows from the definition, right? So remember, when you have an implication, you always suppose that it is true. Suppose that f of n is in this guy and this guy.
Pure fiction.
Yeah?
Nah, nothing.
Okay. So. Okay, so. I mean, right now we just have symbols. Okay? And it means nothing to us. So, why don't we add more symbols? Okay? So, applying the definition, we have a c greater than 0 and an n not greater than 0. Okay, but, actually wait, let me continue. Such that n greater than n not implies that. So this one will be our big O. So your f of n will be less than or equal to cg of n. I think I used d here actually, so let me change that. And we also have that there exists a c greater than 0 and not greater than 0. And we have greater than this time. Okay, now, my question to you is this. Is this n not and this n not the same one?
They aren't necessarily,
Mm-hmm.
Because-
Yes, why?
they could be different functions. Wait, hold on.
The minimal value required for one of the functions to be greater than the other is different.
Yeah. Yeah, that's right. Okay, so if we put them both as n not, it's kind of confusing, and also it's just like bad
Oh.
practice. So what you do instead is
One, two, three.
We can define it as 1 and 2. Okay, and now remember we're trying to show that f of n is actually a part of big theta of g of n using these two guys. So remember that we basically have the entire inequality here, right? So, it's kind. Wait, let me just create the chain real quick. So this is rough work. Put it in a little box. Okay. So from these guys right here, you have that CG of n is less than or equal to f of n is less than or equal to d times g of n. Okay. Well, we have this inequality, which is really nice. So that kind of tells us that, maybe we'll call this D1. No, I don't know what to call this. A and B. Okay. So remember, this is our definition. Try and get used to it. It looks super cluttered right now. I just realized. I'm sorry about that, but so remember that we need to find a C and D constants greater than 0 that are multiplied with Gn. Well, we have constants multiplied by G of n here, so maybe C equals A, B equals D, or let's do that the other way around. D equals B. Okay, but then what about your n naught? Well, remember that in order for these two inequalities to be true, you need that. Let me put it down here. Must have that n is greater than. Okay, let me fix these. N is greater than n1, and n is greater than n2. Okay. So then, in order to get both of them to be true, all you need to do is just let it be the max. So whichever one's bigger, take that one. Just like that. And so if we do that, the proof basically is just complete. So that was just our rough work. Let's actually move on to the actual thing. So if we let C or okay, so you have to say that these two functions, these two constants are defined. So keep these A and B. Okay. Oh, actually, keep these A and B, but also keep N1 and N2, because we need those as well. And then you define your C as A, your D as B, and your N naught to be equal to the max of the two N's. Like that. Okay. Now, okay, we'll label this statement 1, and we'll label this statement 2. Okay, so remember, we're trying to prove that big theta is true. We look at this guy right here. And so what do we need to do? So we've already found our C and D and our N naught values, and now we just need to say that N is a natural number that is greater than N naught. So that's the next part. Let N be natural, and then you suppose that N is greater than N naught. Okay, well, we want to apply our statements 1 and 2. So that means that we need to satisfy these two conditions, right? But we know that n0 is actually greater than both of them, which means that n is greater than n0, which is greater than n1 and n2. So, writing this out is basically like this. So since n is like this, which is greater than or equal to n1, and then also the same thing for n2, and then we'll say by statement 1 and 2, it follows immediately. So we have that a g of n. I'm just rewriting everything now. Alright, and then if we just like substitute these two in, we get this. So then, and then thus f of n is in big theta of g of n as needed. Okay. Okay. So that was a pretty short proof. Like only like half. That's like probably 2 lines in if I were to write this out. 2-3 lines basically. Like 2-3 lines worth of paper. So this one's pretty short. Here's another exercise that I want you guys to try on your own. So exercise. This is like basically practice. We're probably not gonna take this up later, but okay. So recall the definition of an equivalence relation for 102. Recall the definition.
Alex, your mic
Yeah.
is echoing.
Oops. Okay.
Okay. Alright. So how do I want to denote this? A closed relation, let's say this, okay? So what does this have? It has reflexivity, which basically means that everything is equivalent to itself. Number 2, symmetry, which means that if x is similar to y, actually we'll write this out in English. Well, not English, but with more English words. So if x is similar to y, then that means that y is similar to x. So basically the order that you put the equivalence doesn't matter. Okay, and then number 3, transitivity. Hopefully the 102 is coming back to you. So if x is similar to y and y is similar to z, then x is similar to z. So basically the equivalences kind of like bridge each other to each other, like that. So x is similar to y, which is similar to z, which means that x is similar to z. And this is a nice little exercise to try and familiarize yourselves with the big theta, big O stuff. And so basically what I'm asking you to do is to prove that the big theta is an equivalence relation. So let me define this, okay? So we'll have a symbol, okay? Let's call it this, okay? Let denote the, actually, no, I don't want to write like this. Let's say this, okay? Define equivalence as so. So, you have f and g are functions. similar to G, this means that f of n is in big theta of G of n. Okay? And then now, an exercise to do after lecture. Prove that this is an equivalence relation. Okay, and I will not do this. Anyways, here's the entire thing if you decide to screenshot it. Or this is just for the video, I don't know. Alright. There we go. And now we continue.
Why
on.
are we doing 102?
Because it's good for the getting to know the definition.
Oh god.
Yeah, so this one I can take it up like tomorrow or sometime later. But this is pretty good. Okay. So that is big O done. We have finished big O. And now, okay, I think recurrence is fine. Actually, how comfortable are we with recurrence, actually?
IDK.
Okay.
So what is recurrence?
Alright then, we will do recurrence.
Alex,
Yeah.
read request got denied. For 258.
4258.
Damn, that sucks.
Stuck at a 67. So done.
Sad. So sad. Alright. So, number 2, we will talk about recurrences. Notice that I'm kind of taking a long time to like build everything up, so that the master theorem actually makes sense this time. We don't do the Myhabu shit. Alright, so what is a recurrence? What is a recurrence? Okay, well, it's made up of 2 things. Number uno, we have a base case. So basically, there's like, what this means is that there's a concept of smallest unit. So for example, when you're when you're taking a look at the natural numbers, there's a smallest natural number. And in the case of 236, it would be 0. Or in the case of a binary tree, your base case would just be the single node. So that's the kind of the concept of the smallest unit. And then number 2, you kind of have a recursive I don't even know what to put here. Recursive thing. Actually, that's not a good way to put it.
Recursive cases.
Sure, recursive case. I like that. Right? Basically, what this means is that bigger units built from smaller ones. That's what that means. So, actually, we can consider the natural numbers as a recurrence. So, consider n natural numbers. Okay? So, our base case. Well, what's the smallest unit in the natural numbers in 236?
0.
Big fat 0. Okay, now this might be a little bit trickier. We have the recursive case. Okay, well, can we find a way to define every natural number that's not the smallest one as something that's built from a smaller natural number? Well, it turns out that we can, actually. So, every natural greater. Actually, let's write this in math. Okay, so let n. Okay, so we have a natural number n that's greater than 0. Okay. Okay. Actually, okay, yeah, sure. Then, so this one, we'll denote this as like this is like the smaller unit. Smaller unit. Notice how it's smaller, not smallest. So this is, actually, wait, I don't like this. Not greater than 0. Let this be natural. Okay. Then, n plus 1 is also natural. So you see how, so basically this is my recursive case. This guy right here is your bigger unit. And then this guy right here is your smaller unit. So your bigger number is getting built up from your smaller number, which is basically how recursion works. And that's why induction actually works, because you have a base case, which is 0, and a recursive case, where you assume that the smaller unit is true, and then since you can build a bigger unit from a smaller unit, you can actually say something about the bigger unit using just a statement that you know about the smaller unit. So that's the entire basis of induction, and that's a recurrence. And now, there are a lot of things that are recurrences. So you have sets, recursive sets, such as the natural numbers, or you can have recursive structures, like binary trees. Let me write that down, actually. So, recursive sets. So like natural numbers. I can't think of another one. another simple one. Anyways, we have recursive. What do they say? Structures. So like binary trees are a great example. And then we'll talk about the final one more in depth, which is the one that we focus the most on for this lecture / boot the ghetto thing, recursive functions. Right. So this is our focus. This is main focus! Exclamation mark. Alright. So, for example, let's take the Fibonacci. I think the Fibonacci is a classic. I think I spelled it wrong. It's okay. Don't worry about it. So, sequence. This is a sequence. Fibonacci sequence. Which is sus because I said recursive functions, so I'm talking about sequences. But the thing is that sequences are actually functions. They're just functions that go from natural numbers, that have a domain of natural numbers. So let me write that down, actually. So, sequences are
Alex.
Yeah.
Alex, your keyboard.
Uh-oh. Is it actually loud?
It might be
Hold on.
louder than you think, to be honest.
Why is it that loud?
Just mute up. That's what I'm doing.
Okay.
Maybe it's because your mic software is so good.
Oh, shoot. Okay, let me...
Alright. So, sequences are indeed functions. So therefore, we can have recursive functions, or aka recursive sequences, such as the Fibonacci sequence, the GOAT. which actually shows up in the assignment, which is kind of funny. All right. So we'll denote it as f. Okay. So how does this work? F of 0 is equal to 0. This is a base case. F of 1 is equal to 0. This is also a base case. Let me write that down. Base cases. You can have notes. You can have multiple base cases. Trying to think of another example of multiple base cases.
Strong induction.
Well, yeah, but I'm trying to think of a more intuitive example. Like maybe from a recursive set ish. Okay. Oh yeah. So this one's actually a little bit counterintuitive, but how about let's go off to the side actually. Tangent. Multiple base cases. So, how about we define a set as follows? Okay. So, let's say that the number 5 is in your set S. Okay. And now, let's also say that the number, wait. Yeah, okay. So, number 5 is in your S. And then, let's also say that negative 6 is also in your S. And then, so these are your base cases. And then you can define it recursively as follows. You can say that for any arbitrary 2 in S, wait, I don't want to do it like this. Okay, let's not do it like this then. Actually, wait, yeah, sure, why not? Okay, we'll do it like this. For A and S, so this A is anything that's in the set, okay? So for A and S, then 2A is also an S, okay? Now, if you define a set like this, then you need to have 2 base cases, okay? The reason why is because imagine you could have defined this set another way with just 1 base case, okay? So that's like, choose one of them, okay? So you can choose 5 or you can choose 6, okay? But then after you do that, you have no way of getting the other number through the recursive case, which is why you need 2 base cases sometimes. So in this example, in the Fibonacci sequence, you have 2 base cases. F0 is equal to 0, f of 1 is equal to 0, and then the famous part of the Fibonacci sequence goes Fn. This is Fn minus 1 plus Fn minus 2. So just the previous 2 terms. So this is for all n greater than 1. I'll say for all. All n greater than 1. Okay? And this is your recursive case. And, oh god, computer programs eat this fucking shit up, okay? Because when you're doing recursion, kind of models this kind of structure perfectly. So you have your base cases, more than 1 possibly, and then you have your recursion, your recursive case, which breaks it down into the smaller units. Right here. Why is my pen not drawing? There we go. So this is an example of a recursive function. And now, the thing is that when we're concerned with recursive functions in CSC236, we care about finding the runtime of these recursive functions. And it's not as easy as a normal function where, let's say, you have a function f of n is equal to n log n this thing squared, and then literally you can just find any upper bound. Doesn't even matter. You can literally define it to be the upper bound of itself, right? That works. But you can't really get a nice form for this guy without doing extra work. So it's very hard, not very hard, but it's a little bit more tricky to do runtime analysis on a recursive function. So there are actually two ways to do it. Two ways to runtime anal. Is it slash first? I don't remember, whatever. With recursive functions. Okay, number one is find a closed form. And number two, guess what it is, guys? Guess. You're never gonna get it. Guys, it starts with an M, and it goes to an A. Masaru. No. Master.
I'm sorry. I think oh my.
Yeah. So we're gonna talk about this first. Both of these are in the assignment, by the way. So it'll be nice to cover both of them. So we'll start with number one, finding a closed form. So closed forms. So what exactly is a closed form? Well, all it means is that you have let's say you have any function, okay? And basically, you just want to be able to define that function. Just want to be able to define the function using what basic structure. I don't know if that's the right term. I'm pretty sure there's a formal definition for closed form, but I'm not that good yet. So basically, you can define the function using basic structures. What does that mean? Like addition, subtraction, like multiplication, division, normal ass numbers, not recurrence. Yeah, so basically just find like an obvious way to calculate the function. The way you know that you have a closed form is if it's really easy to evaluate your function. So if you have the Fibonacci sequence, okay? Like if I tell you to find F10, like and as well I tell you to do it in like half a second. Like that's like what the fuck? But then what if I told you that it has a closed form of this? Okay, well, this is actually 1 over root 5, and then yeah, this is true. Do not worry about it. Okay, and then you replace the n with a 10, and then like it doesn't look simple, but I wrote it out and this is an actual number that you can put in a calculator and calculate. Like if you put in f10 is equal to f9 plus f8 into a calculator, it's probably not going to know what the fuck you're talking about, right? So that's kind of what a closed form is. I don't know why I erased that. That's kind of stupid. Let me put that back. Okay. So yeah, so closed forms are great for finding runtime. Okay, now let's do an example. So, let's say you have, let's f be a function defined recursively. Okay, so you have, let's make it a piecewise. Okay, and let's give it a base case of 69 if n is equal to 0. And then let's say that it is f of n minus, let's do 42. 42 times f of n minus 1 when n is greater than 0. Okay, well, you have a recursive function here. The way you can tell it's recursive is, well, it has itself, but smaller in it. And as well, you also know that it's not in closed form, because if I ask you for f of 10, like, you're gonna say, oh yeah, that's literally just f of 42 times f of 9, yeah, whatever that is. So, no, it's not in closed form. And so, one of the ways that you can find a closed form is you can use something called, you probably can't read that, repeated substitution. Okay, so what does this consist of? You'll never guess. Substituting repeatedly. Isn't that crazy? So, the way we do this is you take an n in the naturals, okay? And you just say that it's like arbitrary size so that you can just keep like substituting repeatedly, right? Welcome, Bill Do.
Hello, Bill.
So, you can just do repeated substitution on this guy and find it. So, you take random natural number and you say, okay, so I want to try and find f of n. Okay, so let me just apply the definition to this guy, right? So you have 42 multiplied by f of n minus 1. Hello? Very nice. Okay. Alright, so you have f of n is equal to 42 times f of n minus 1. Okay. But this is, I'm nowhere close to finding out what this closed form is. Right? So then, okay, so what if I do the substitution again? So by using the definition, I get 42 times 42 times f of n minus 2. And I'm like, okay, sure, let me do it again. So then you get 42 times, I can't, okay, 42 times 42 times 42 times f of n minus 3. And it's like, I think I kind of see what this is. And then like you like keep going if you want, or if you see the pattern, you're like, oh, let me make a guess. So when you do repeated substitution, you take a really large number and then you break down the function with this recursive definition until you find a nice pattern. And then when you find that nice pattern, you're going to make a guess at what the closed form is. So by looking at this function, it's like, oh, you're just like multiplying 42 by it every time you go down an n. Every time you go down by 1, you multiply by 42 once. So why don't we say that f of n is equal to 42 to the n? Seems reasonable, right? Like, I mean, like, it multiplies by 42, and, like, it keeps going forever and ever and ever, and it never stops, so then this is just that, right? Okay, but then now you have to show that it works. Okay? So then, show that it works. And how do you do this? Well, week 1 and week 2. Okay, so let's do this because, okay, spoiler alert, this is not right. Base case n equals 0, which is our base case. So remember that your f of n is equal to, or we claim, where's my erasing? There we go. What are we claiming? What is our claim? F of 0 is equal to 42 to the 0, which is 1, but we know that, but f of 0 is 69? I don't know. So then you go back to the base case and you see, like, oh, when n is equal to 0, we want it to be 69. So basically, you go down and down and down, and you multiply by 42, and you keep going until you reach your base case, which is n equals 0, and then you multiply by 69. So now you can get a correct guess. And this is f of n is equal to 42 to the n multiplied by 69. Okay, so now we proceed using induction. Okay, so remember, as always, to label your guys properly, your sections, because I lost the mark on that for some reason. Horrible people. And also make sure to specify what exactly you're doing induction on. So right now I'm doing induction on n. So what is your base case? Smallest unit, which is 0. So we go off of the definition of our function. I cannot spell. By definition, f of 0 is equal to 69. And then this is our closed form, and we want to basically show that this is we want to show that this is equal to 69, which is true, because this guy just goes to 1, right? And then that's your base case done. And now you can do your induction step. Not induction hypothesis. Whoops. Induction hypothesis. Okay. Well, that means that you say that, well, hopefully this is fine. So suppose that closed form, I think you're supposed to do a predicate for this, but I'm too lazy, so holds for some k in the naturals. Okay, you don't use the same letter here, or at least I don't. I think that's dumb, and it looks bad. It's kind of confusing as well, so I use a different letter here. So what exactly does this mean? What does that mean? That means f of k is equal to 42 to the k times 69. Okay. So, what do we want to do with this information? I have f of k is equal to this guy, but what is that going to do for me? Well, remember what we want to show. We want to show that f of k plus 1 is actually equal to this. Okay, great. And now we do the induction sutepu. We are almost at master theorem, guys. Just a little bit more. Okay. So, we'll do the left side. Actually, I lied. There's no left side. So, by definition, you have that f of k plus 1 is equal to 42 times f of k. And then, by your induction hypothesis, you have that, I guess we just rewrite the entire chain. This guy is equal to 42 times f of k, which is equal to 42 times 42 to the k times 69. And then this just works. Wow! Wow. It just works. So then, by induction, I don't know what I'm doing. Okay. By induction, closed form is correct. That was a very simple example, but I hope that made things a little bit clearer as to how you find these kinds of recursive functions. Okay. So like these ones are pretty simple. If you have, where is it? If you have like a linear function like this, it's pretty simple to just kind of like repeated substitution your way into things. Do I want to show? No, okay, no, let's skip it. But I was gonna say that if you have a recursive definition, something along these lines, like you have a constant times f of n minus 1 plus another constant times f of n minus 2. There's actually a method to find the closed form of this guy, and it uses some funky magic that I don't think I'll be able to explain to you. So we will not worry about this because it's not related to whatever the fuck we're doing. Alright, so now let's talk finally about the main topic about what we were here for all along.
Ooh, master theorem, finally.
Master theorem. Okay, so master theorem. The motivation behind master theorem is to find runtime, or wait, no, to analyze runtime of recursive programs. Okay, so but master theorem doesn't work for every type of recursive programs. What type does it work for? Okay, well, recursive programs have a recurrence for their runtime. So, for example, there's no way I'm about to code in fucking pencil again. Fuck me, dude. Okay, sure, let's do it. Okay, so you got a function and it's called factorial. Okay, great. Factorial int n. Great. Okay, why am I doing Java and Python? I'm stupid. Okay, so you have factorial n, and basically, I'm just going to write this out really quickly. Okay, so this is a recursive program. Why? Because you have a base case and you have a recursive case. Okay. Well, can we find a recurrence for this guy? So when we talk about a recurrence for a program, that's not how you spell program. When you talk about a recurrence for a program, you're talking about this means you want a recursive function for the runtime of the program. So what that means is you want to find basically how long it takes this program, or how many steps it takes this program to return you a number. Okay, so this is a very simple example, so I'll just show you. T of n, which is what we'll define as the runtime for factorial. This guy, okay, well, first of all, we deal with the base case, and it literally, all it does in the base case is it just checks if this guy is true and then returns 1. And that's a constant time thing, so we'll just call it 1. Just for simplicity's sake, we'll call it 1. This is when n equals 0. Okay, so then your next case is when n is greater than 0. Okay, well, what do? You go through this line, you check the condition, it's not true, and then you go to this line, and then you return this guy. Okay, well, remember that this n is actually, when you multiply n by something, it's not actually linear time. So, let me just move this to the side a little bit. Can we erase? Okay, there we go. So, first of all, not only do you have the runtime of the previous iteration, not previous iteration, the smaller unit, but you also have your guy here, which denotes the time it takes to multiply. So this is multiplication time. Multiplication steps, I guess? Sure, we'll call it multiplication steps. So notice that in all your recursive runtime for a program thing, you always have your recursion part, and then this is, I don't know why I deleted that. And then this is your extra steps part. So, for these guys, you can actually do repeated substitution to find the closed form. I think, don't quote me on that, I think you can use that to find it. Yeah, it should work. So, you can do it. I'm not going to do it. I'll do it. I'll leave it as an exercise. Find closed form for T of n above. Okay, and if you want a screenshot, go for it. Okay, boom, we're done. Alright. And now, yeah, so this is pretty simple, but, okay, remember that, okay, now we'll go back to master theorem. So master theorem only concerns recursive programs of a certain type. Which is not this. So, what is this? So you have a guy, T of n, and you have a base case, constant C, and okay, so this one right here is the base case, but this is actually like just simplifying things a little bit, because your base case is not always guaranteed to be like size 1, right? So this is simplified. And it shouldn't really change anything in the long run because this is a small value, right? And when you're talking about runtime analysis, you only care about big values of it. So simplified, but works. Okay? And then, what is your recursive thing? Well, basically, here we go. So you have this part. Basically, what's happening here is you're basically splitting your original input into multiple pieces. How many pieces? Exactly B of them. And you're also having, but you also split them. You make your input smaller by this much, but at the same time, you actually have 8 different recursive cases, which doesn't really make that much sense, but let me explain it to you. So, and then you also add it by Fn, which is these are your extra steps. Like I said before. So extra steps. So, why can A not be equal to B? Well, there was actually a fast multiplication method that's in our assignment actually, so this is this might be a little bit interesting to look at. So fast multiplication. Okay, so this is a specific case where your A is not equal to B, and don't ask me for another example because I can't think of one. I'm not that good. So fast multiplication. What's the deal behind this? Okay, so basically, why complicate multiplication? Okay, I cannot implement the method on my thing right now, so hold on. I have an idea. Okay, wait. This is gonna be really incriminating. If I open my Safari right now and something bad shows up, I'm gonna cry. Okay, we're chill. Okay. So let's take a look at the Karatsuba algorithm, because that's what we're concerned about.
Oh god.
Let's see here. Here we are. Ah, yes. Okay. Can I open this image? Okay, whatever. But basically, that looks ugly. Can I find a better one? Okay, not really. But, okay, I'll explain it to you. So, why complicate multiplication? The reason is because multiplication is slow. At least in programming. At least in coding, like computer stuff. Multiplication is slow. Specifically with big numbers. Which is why, so that motivates recursive multiplication. Which is kind of crazy to think about, right? Like, how does anybody think of this? Alright, so here's how it works. Okay? Let's say you have what letter do I want to use? X. So let's say you have x times y. That's confusing. X dot y. Okay? And then equals what? And you want to say, and then let's say the x, y are huge numbers. By huge, I mean a number that you have never thought about in your life. A number bigger than any number that you've ever thought about in your life. And the moment you think of that number, it gets bigger. Okay, so that huge, okay? So, and when you do multiplication like this, well, what exactly is multiplication? Well, it's just like repeated addition, right? So like so if I were to kind of like give you an example, this is like kind of like x times 1 plus, wait, no. This is like x plus x plus x plus x, and how many times do you do it? You do it y times. Okay, but then, isn't that kind of crazy? Like you have to do it this many times, and y is a huge number, so it's like, what the fuck? So you can actually split x and y into smaller numbers. How do you do that? Well, you can write x as equal to this guy. You could say is p plus q, right? For like arbitrary p and q, which you can choose, by the way, in the algorithm. And in the algorithm, they choose them so that they're close as possible together. Not like size wise. Otherwise, you would just choose them to be equal to each other, and so like they would just be like x over 2. So not p equals q equals x over 2. Similar digits. So what does that mean? That means that, example, let's say you have like 1, 9, 4, 3, 2. Let's add one more digit. 9. Okay, so what does this guy turn into? Well, the Karatsuba multiplication, it chooses like, you like split it right here. So you split it by digits. So then you actually get 194000 plus 329. Which is interesting. Like, you might think like, how the fuck does this help? Right? And it's like, Okay, but anyways, so you have your x is equal to p plus q, and you have your y is equal to r plus s. Okay. Great. What does that do for us? Well, remember from high school, what is p cubed times r, p plus q plus r times s? Okay, well, you'd use shit, what do they call it, bro? In Ontario high schools, they call it the FOIL method. So you just like, you do like, alright, I'm gonna teach you guys high school, Ontario high school math. The trashiest shit ever. So, real quick. First, fuck, I can't type, or I can't write. Out, in, last. Okay, so you multiply the first ones, and you multiply the outer ones, and you multiply the inner ones, and then you multiply the last ones. QS, okay. Alright, so, this is, yeah. So, you have xy is equal to this guy, which is equal to this guy. Okay, so you just defined one multiplication. You split it up weirdly like this, and then you expanded it and you turned it into 4 multiplications. Like, what? What the fuck are you doing? Okay, well, turns out that this is actually pretty fast. Wait, hold on. Am I even doing this correctly? Let me look at the algorithm. I forgot. Shit. Am I cooked? Yeah, I think we should be fine. Okay. So, this is actually faster. This is faster than doing it normally. Okay? And in this case, I'm definitely missing something. Yeah, I'm definitely missing something. Wait. Let me go to... Oh, shit. I need to look at the code again to remember. Whoops. this was I didn't plan to cover this, so it was kind of unexpected on my end. Okay, we can go to the
grades.
introduction
The
to
grades.
theory of computation, and then we go to page. Fuck. I don't know why it does this. Page 43. Exactly page 43 because it's right here. See? I planned this out. Okay. So. Yes. Okay. I remember now. Basically, you have PQ plus RS and then AC. Okay, so what it does is you take this binomial expansion and okay, let me write this out. R plus S, and then you do minus PR minus QS, I believe, because wait, so R times plus what am I doing, bro? Holy fucking shit. So you minus that, and then you get this. Okay, whatever. The it doesn't matter. Okay, but basically, what does matter is that this is faster. I don't really want to explain it. Okay, so, but if we look at the algorithm itself, so look at this n. Okay, you see that little n there? That's your size. That little guy, that's your input size. Not x, not y. N being the number of digits of both of the numbers, and they have the same length. Okay, and basically what happens is every time you make, where is it? Okay, every time you make a recursive call of this, you always cut the number of digits in x and y in half. The way you do that is, with our previous example here, what happens here is you actually turn this into like 194 and 329. So you basically just cut the digits in half, which makes multiplication faster. Because okay, so imagine going down from like let's say like this many steps down to like this many steps in just like one recursive case. Like that's really fast. When you do it with just like regular multiplication, you do like, let's say you start with this number, one more zero. Okay, so you start with this number, and then after the next step, you only go down one. Yeah. Okay. Anyways, that's like enough intuition, probably, and then it works. But notice that you cut the number in half. You cut the number of digits in half, but you make 3 recursive calls. And that's kind of why A is not necessarily equal to B. It's intuitive why that would be the case, but it's actually not. Anyways, that was a horrible explanation, but I hope you learned something from that. Anyways, let's move on. So, in order to do runtime analysis on this guy, I'm going to rewrite the formula. Here we are. Okay, so in order to do runtime analysis, in order to do runtime anal, okay, it would be nice if we could find a close form for it. Actually, you know what? Let's start with the master theorem. Start with the statement of the master theorem. So, let me just move this all the way down. Okay, so this is the master theorem. Okay. If your Fn is in O of n, okay, n to the k, where k is greater than log BA. This will all make sense, okay? Trust. I will explain this. Okay, then T of n is in theta of... Am I good at this? Was that n to the k? I hope it was. Okay. And then if this guy is theta of n to the k, where k is equal to log BA, then your Tn is theta of n to the k times log B, or it doesn't matter, log n? I mean, if I'm wrong, I'll find out later because of the proof. Okay, and then finally, if Fn is in omega, that looks horrible, omega of n to the k, where k is less than log A, log B of A. Oh, and there's an extra condition here, and there exists a c less than 1, or a... So basically, that there exists a c in between 0 and 1, such that... Oh, I have no space. It's okay, I'll just zoom out a little bit. Okay. Such that c times f of n is greater than equal to f of n over b. This is called the regularity condition. Don't ask me what it means, because I have no clue. But I think what it means is that as your inputs get smaller and smaller, the time that it takes to run your extra steps doesn't really change that much. That's basically what it's saying. And we'll just continue moving this down. Okay. So that's called the regularity condition. I'm gonna put this above. Regularity condition. Then your T of n is in big theta of n to the... Fuck. Wait, no, this is... Okay. And this is n to the log BA. I think. I'll figure out if I'm wrong or not. Okay, so that's master theorem, and it looks horrible. It looks fucking scary. You know, I can't lie. I shot my pants the first time I saw this. Okay, and then I looked at my havu, and then she looked at me, and then she like sent me to heaven, and then I understood it. Yeah. Okay. Anyways.
She unshot your pants.
Yes. Exactly. My turds went to heaven, and then I came back down. So, this looks fucked up, but I will like try to explain it to you in the best way possible so that it is not as fucked up. So, in order to do runtime analysis, we should try to find a closed form for T of n. Okay, and now we will do it using the only way we know how, which is repeated substitution. Okay, so let me rewrite the definition for this guy. Okay. So n equals 1, and then this is a, t, and number b plus this guy, and greater than 1. Okay, so repeated substitution. Fun stuff, yeah? Okay, so t of n, this guy is equal to this, and remember we have to keep everything as letters, okay? So you're not gonna see... Okay, wait, I'm going through the proof right now in my head. You are not gonna see a single number in this proof. Actually, you'll see 1 and 0, but that's the only number you'll see.
Bro, right. Ethan is his own stockfish chess program. Like, you can see the future of the proof.
Okay, so you have this, and then you have the next recursion thing. So we'll put a bracket here, and then this becomes n over b squared. Oh, I guess you'll see it too, because we're doing repeated substitution, but that doesn't count. Okay, f of n plus f of n. Okay, and okay, by the way, remember, n, this guy is an integer, right? N is natural, not an integer, sorry. But then we're like dividing it by like this random guy called b squared. So like how is it that this guy always stays a natural number, and like it doesn't always stay a natural number, but you just you just make n nice. You know what I mean? So that it keeps staying a natural, and then you afterwards you can do something called interpolation to like figure out the time complexity for everything in between, which I don't want to talk about, so we'll just keep that there. Then use interpolation to fill in gaps, and I'm not gonna go more in depth because yeah. So, anyways, moving on. Let's simplify this a little bit. Simplify this guy right here. So this becomes a squared tnb plus a f of, oh wait, this should be n over b. Yeah, n over b plus f of n. Okay, and okay, I'll do it one more time, and then I'll tell you the pattern. So one more time means a squared times a t to the, oh my god, I love writing. Fun stuff, fun stuff. And now I'm simplifying. Okay, this is this. Okay, and then da 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 da. You get down to t of n is equal to. Okay, I'm gonna write it down, and then I'll explain why. Okay, so you have a to the log bn multiplied by t of 1 plus the summation of I, starting from I equals 0 to the floor of log base b of n, a to the I multiplied by f of n over b to the I. Okay, so I'll explain this now. Basically, theoretically, you can do repeated substitution until this inside gets to the base case. Okay? And remember, we say that our base case is 1. Okay? So, remember, note that the base case is n equals 1. So, now, the question is, how long does it take you? How long does it take you to get to the base case? And to do that, we can just solve for this guy that we call L, and we can do a little bit of AP magic, right? And then we can get that L is actually equal to log base b of n. And of course you
Hold on. Sorry if I may interrupt. Can you scroll up for like a few seconds? I want to see what happens for in the past 2 minutes.
Okay, sure. How much do you want me to scroll up?
Upwards is yeah, just here. Okay, so that's basically the formula for the master theorem, right?
Yeah, correct.
Okay, that makes sense. Cool.
Alright. Yeah, so you can just solve for L using algebra, and you get that L is equal to, oops, this guy, but then you want to make it look nice, or you want to make it an integer, right? So then you just change this into the floor. Yeah, so then that's where this guy comes from, right? See that guy? Yeah, so that's where he comes from. And technically this is also supposed to be floored, but my Havu is a great person, so yeah. Alright, now let's talk about why this makes sense. Okay? So remember, you have I'm gonna just start drawing pictures now. So you have something like a size n guy, okay? Alright, we got some UML diagrams going on, okay? And okay, let's take for instance the fast Karatsuba multiplication, where you have A is equal to 3 and B equal to 2, I think. Okay, so then that means I don't like this. 2, 3, let's swap them. So that I can draw less arrows. Yeah, that's why. So then you split this into 2 cases. And then you split this into 2 more cases. And I think this is as deep as I'll go because there's no way I'm doing more. Okay. So. And, okay. Suppose this is your base case. I'm getting a little bit lazy, but this is your base case, okay? And so, this is your base case. T of 1. Imagine that this is your T of 1. This guy right here. This guy. Okay, well, how many of these base cases do you have? Well, your formula says that there is a to the log b of n of them, but why exactly is that? Well, remember what log b of n is. Log base b of n. That's your L. That's how many times you apply the recursive formula, actually. Because that's how many times that you need to divide n by b in order to get the number 1, which is your base case. So, you go down 1, 2, 3 times. So, your L is equal to 3. Right? So that means that by this formula, right here, you will have A to the 3. I missed something. Fuck. I think this is 0, 1, 2. Yeah, that makes more sense. Okay. Yeah, so A to the L, which is log base b of n. So that's 2 to the 2, which is 4. Notice that we have 4 base cases. Basically, this left part right here, that's the time it takes to compute all your base cases in your recursive algorithm. So you have your original recursive guy, and then you break it down all the way down using repeated substitution until you find the explicit runtime for your base cases. Okay, but then what's this like fucking ugly shit over here? What is that? Okay, well that's the time that it takes for you to combine your base cases together. So remember in merge sort. Okay, let's talk about merge sort. Real quick. You have you split the list. You split the list, sort, then merge. Okay, well, your merging takes time though. And that's basically what this f of n is. And actually, the entire key behind master theorem is that it's saying that the time complexity of your extra steps largely determines the runtime of your function, which is kind of interesting. But it's basically saying that the extra steps are very important for determining your runtime. So, going back, this is the number of times that you need to merge your input into the bigger one. And so, what is this crazy ass number? Okay, well, let's start from. Okay, let's say that I is equal to 1. I'm gonna skip 0 for now, okay? So I is equal to 1 means that you have that your inside term will be equal to a. Oh, shit. Will be equal to a to the n over b. Okay, what is that? Well, this guy, remember, this is number of steps. What the fuck? Number of extra steps. When working with size n over b. Okay. Well, let's take a look at our example again. Your b is equal to 3, and your I is equal to 1, which means that you have divided once by b. So you divided once by 3. That's this level right here, level 1. So this this fn over 3, that's basically talking about how much time it takes for you to compute all the extra steps when like dealing with this guy right here. This guy and this guy. And since you have 2 of them, you multiply by 2, which is actually exactly equal to your a value right here. See this guy? Yeah. That's why the a is there. And so notice that as you increase the terms, so once you go to a squared n over b squared, well, now you're at depth 2, okay? And you have a squared base cases, which in this case would be 4, like 2 squared is 4. So you have 4, not base cases, sorry. You have 4 data sizes of size n over b squared, which in this case is n over 9 in our example. And it's saying that you have that processing these input sizes of n over 9 takes some amount of time, which is denoted by f, by the function f. And then since you're processing that information 4 times, you multiply by the a squared here, which is the number of different data sizes that you have here. And yeah, and you just sum them all up from each depth. So this sigma basically just represents each depth level. So at the bottom depth, you're processing a certain amount of steps, and in this one you're processing a certain amount of steps, and then in this one you're processing a certain amount. Just like that. And that's kind of like where the intuition for the closed form comes from.
A question.
Yes.
So that means that for analyzing the runtime with the master theorem, the tree that is created from that is always balanced, right? Most of the time.
Only for nice values of n.
Nice values. Okay.
So remember for merge sort, right? If we draw a diagram for merge sort, if you have an odd number size right here, right? You split it into like a data size of 2 and 1, which is like, and then this one goes into 1 and 1. Right? So
Yes.
yeah, so this is like nice for nice values of n, and then there's odd cases like this where you kind of get this like unbalanced guy here. But like those smaller cases, they don't matter too much to the master theorem because you only care about the master and not the slave. All right.
Okay, so basically the master theorem only cares about the big numbers, basically.
Yeah, that's like runtime analysis in general.
Oh, makes sense. Yeah.
Yeah. And so my Havu and whoever decided to give us CSC236 blessed us up with nice values of n. So thank them, because otherwise I would not be here teaching you guys this, because I would also be struggling. So yeah. Okay. So does the closed form make sense? First of all, before I move on.
Looks so. Looking at it.
All right.
Wait, just to recap, the the log, the upper thing for this summation, that's the number of deaths.
Mm-hmm.
The L,
The L is the number, is like the depth number basically. So like the number of times you like go down the recursive step.
that's completely separate from the actual closed form, right? It's just to show. It's just to
Well,
show how the upper thing came to be.
you.
I guess it's not separate.
I mean, your L is exactly log B event, which appears in
Oh,
the
yeah,
closed
yeah.
form. Yeah.
Oh, you call it the L. Okay. Okay.
Yeah.
What's the A and B?
So if we remember from this, so B is the factor that we chop down our input size in. So you chop
Okay.
it into B piece or I wouldn't say that. Okay. You just make your data size smaller by a factor of 1 over B every time you call the
Okay.
recursive step. But your A is the number of recursions that you do in one depth. So remember how I was talking about... Actually, she's merge sort again. So for merge sort, you have your n right here, and then you always split your data size into 2. And also into 2 parts as well. So in this case, since you half your data, you cut your data in half, your b is equal to 2, but you also have two distinct pieces of your data. So then that's a equals 2. So that's where the a and b comes from. It's just straight from the function right here.
Okay.
Okay, let's see. Is there anything?
Quick question.
Yeah.
Will the lecture notebook be posted with the recordings?
I can try, but the thing is that this notebook is combined with a bunch of other random shit that I put in here.
Are you not able to export this
I
alone?
can. I think I
Alex.
can export it, but it'll take a while.
Okay,
Oh
no
shit!
rush.
I'm getting spammed in Discord. It's gonna show up in the recording. I gotta turn on do not disturb. Okay.
Oh.
By the way, you should probably charge your iPad. It's already low.
Yeah, I know.
It's not that bad. It's 19.
Okay.
Wait, Richard, what were you saying?
So if you look at the in the VC chat, I sent a picture of my notes, which denotes each variable's meanings. If you want, like, take a look at it.
Oh, you documented it. Yo.
Yeah.
That is very nice. Yes. Okay. I don't think I'm missing anything, so we can start runtime analysis. Okay, so I'm gonna rewrite the function here. Okay. Plus I equals 0. Okay, so this is my first time actually writing this out, so this might go very badly. We'll see. Because we're getting into the juicy stuff now. Alright, so I want to take a look at this term for a second, because we have n in like the exponent, like the log of the exponent, which is kind of sus. So let's just take a look at this term for a second. Okay, well, we know from logarithms in high school that a is equal to b to the log base b of a, right? So then this guy is actually equal to, if we just do a substitution, we get this. And then by exponent rules, you can actually flip the order of these, right? And then notice that like this guy is in the exact form of the thing that we have here, except that instead of a we have n. So this is actually just equal to this. So we basically just swap the places of n and a. Right? And we love having n in the bottom. So I'm going to rewrite this once again using our nicer notation now. Because the reason why we do this, okay, well, imagine trying to find the, without knowing this, like this like kind of like swap thing, imagine trying to find the runtime complexity of this guy, like, and you're probably like, what the fuck is this? What is this? But then once you have like this nicer form, it's really easy to just like immediately just see it, and it's like, oh, this is like O of log base b of a, which is like really nice. So that's why we do that. Anyways, I'm just gonna rewrite the log here. AI. This guy. Okay. So, all right. So we will start with the first part. First half. I'm reluctant to say half because I don't think it's really half, but since we have a sum here, we're gonna look at the sums individually. And then once you combine them together, whichever sum has the bigger, like faster growth will determine your big theta basically. So let's talk about this. This log this guy. T of 1. Okay, well, okay, just by looking at it, can you tell what the, actually not the O, let's talk about the big theta. So what is the tight asymptotic bound of this guy, just by looking at it? Okay, well, you have T of 1 here. What is this guy? This is nothing but a constant. And then the only thing that depends on n here is this guy. So it should be pretty easy to see that this guy is actually big theta of n log base b of a, because this is like n raised to the power of like some random number. So like it could be like n to the 1, n squared, n cubed, anything, but instead of like those regular ass numbers, you have like log base b of a. It's just a number, okay? So, and remember your t of 1 is a constant. It doesn't have any, the runtime of t of 1 doesn't increase the more you increase n. So, it's just a constant. You can basically ignore it. And you only care about this. So, see? First half, guys. We're already halfway there. Isn't that amazing? Okay. Now here's the second 90%, okay? We talk about this guy. Alright. So this will be fun. This will be very fun. Trust me. Fun for you guys because you don't have to do anything. But okay. So your first step is we make the assumption that f of n is actually big theta of some guy, and this some guy will be n to the k. Okay. So this is an assumption, and we'll make use of that assumption. So recall from the definition, there exists a c greater than 0 and an n not greater than 0 such that n greater than n0 implies that this guy n to the k. Okay, so it would be really nice be really nice. Actually, let me. Yeah, let's do n. Because I don't want you guys to get confused about the variables. So we're gonna use another variable here. Do not worry. It means the same thing. It's just another letter. It's just another letter. It's like if I came to school the next day, but I wasn't Asian. Like, would you still love me? Okay. So.
It's
So you have this, and I'm gonna remove the absolute values because I'm gonna assume that the runtime of this guy is not negative, because that would be very suspicious. So it would be really nice. I will say this. It would be nice if we can let m equals n over bi. Because then how do I want to write this? We get, oh right, this is big theta too, so I kind of fucked up. Okay, wait. CD greater than 0. Okay. So you have CMK. That was my bad. Okay, so then, if you can let m is equal to n over bi, for all I, we can really easily just get this inequality. Not m. Sorry, this is a over bi. Because remember, we're doing this term by term. So bi to the k less than f of m over bi is equal to my iPad is dying so fast, that's crazy. Okay. Anyways. Yeah, so it would be really nice. What is the problem though? Okay, well, remember, you need this condition to be true. That's why. Right? So is it guaranteed that this guy is greater than n naught? No! It is not. Okay, well, okay, I'll add for all I. Is it guaranteed that for all I, n over bi, n over b to the I is greater than n0? That is not true. But we can say that this is true for some I. So that means that we basically split this guy into two. So so basically in one side we'll have everything such that like this value is greater than n naught, and the other one will be all the other ones that are less than or equal to it, where we can't apply the definition for the big theta. And it turns out that the one that you can apply it to is actually easier to do, which is kind of funny. But okay, well, how do we know where to split this list? Okay, well, best way to do it is to just solve this inequality. So I will do this now. I will do this for you. So we will solve for I in this guy. Okay, well, what do you get? How guess how many steps I want to skip. None. Okay. Let's bring the bi to the right side and then the n naught to the left side. Okay. So you get that. Okay, that makes sense. And then I'm gonna like just flip the inequality. So I'm gonna put the bi on the left side. Actually, no, I don't want to do that. Let's apply log to both sides. Because remember, log is... Okay, never mind. We can apply log to both sides, and it keeps the inequality, okay? So, log of n over n naught is greater than log of bi, okay. And then by log rules, you can drop the I down. So then this becomes log n naught is greater than or equal to I log b. And yeah, you're supposed to do log base b here, right? So that this guy disappears. And so you actually end up, if we flip, reverse the inequality and kill this guy, then you get that I is less than equal to log n over n naught, but this guy is actually using log rules. You can say that, I need to put base b here, keep forgetting. Okay, you can say that this guy is actually log base b of n minus log base b of n naught. So that means that I is less than this guy. Okay. But, okay, this is not necessarily an integer, which is a problem, right? What we do know, though, is I is an integer, which means that the inequality doesn't change if we just apply the floor operator to the right side, because okay, let's take a look at a number line. Okay, let's say our I is right here. Okay, and then this is your actually I'll say 10. Okay, so this is 10. This is 11. And then this is like 10.5. Okay, so, and I'll put 9 over here. So if this is this is where your I is at, and then I just write it down, I guess. Log bn minus log bn naught. Okay, so it is here, and then you apply the floor operator. Well, it just goes to 10, right? Okay, so like there's no problem with like I is far away. Okay, but then you might be wondering, okay, well, let's put I at 10. Then it just like drops down, and then it becomes less than or equal to. Okay, but like, what happens if like it jumps past I to 10? Okay, well, I is an integer, right? So it can never be in between 10 and 11, which is why you can just apply the floor. So therefore, you get that I is less than or equal to this. And that's like your split. That's where you split the list. Or not the list. That's where you split the sum. Oh my god, I'm brain dead. Okay, so I just wrote on like 1/2 of the fucking thing. Why did I do that? Okay, anyways. So I'm gonna rewrite the sum. I from 0 to the original thing, log bn of ai times f of n over bi. Okay. And then we can use the summation thingamajiggies. Okay, so this goes from 0 to this guy. Okay, so log base b of n minus log base b of n naught, and then floor it. Like all of this just looks like complete garbage if you're looking at it for the first time. I can't lie. Then you add with the continuation of it, which is I is equal to this garbage plus 1 actually. This garbage plus 1. Oh my screen. Okay. And we'll put it all the way over here, I guess. And over BI. Okay. Well, so I did say that the second half is easier. So let's do the second half first, okay? So, in this, how do I want to do this? Okay, let's just move to the side, okay? Oh god, I don't want to write this again. Okay, whatever. Let's just consider the arbitrary term. Consider the arbitrary term AI times f of n over bi. Okay. Well, this is a term. This is a term from the second list, right? And what do we say about why we wanted to split this? Why do I keep saying list? Sum. Okay. So what was the reason that we wanted to split this sum into two? Well, we wanted to have one side where n of bi n over b to the I is greater than what was the number again? N0 and not. And then the other side into a side where we can say that it's less than or equal to n naught, so that we can apply the big theta thing to the first one, and then just figure out some way to deal with the second one. I don't know why that happened. Okay. Okay. So that means that that n over bi is less than n. So in this list, or in this sum, it is true that n over b to the I is less than or equal to n naught. Okay? And this is the key part. It's constant. This is a constant, guys. So you have something that you have like these guys, or not, like all of these n over b to the i's, all those different possibilities that you can have for I, doesn't matter, bro. You have it bounded above by a constant. So since it's bounded above by a constant, what that means is that f, this guy, is bounded. Right? And I mean, it's very intuitive to say that, right? Because you have like the input is bounded, so then the function must be bounded, right? But sometimes that's not true. I can give you a counterexample. Like if you have just like tan, right? Tan x, but you set the domain to. Okay, never mind. I think this counterexample is gonna just make things confusing. Okay, well basically, this guy. Remember that n is a natural number, right? So, so there are finite possibilities. There are finite possibility of values for this guy, because we already have that this is bounded below by something. So there has to be at some point where, like, once you increase this n enough, it stops being valid. So this guy it has like a maximum basically. So it has maximum. Also, sorry, I said something wrong. So I said that if you make n bigger, eventually it'll be like whatever. That's wrong, because n is actually fixed from the beginning. I forgot to mention that. Sorry. So misconception. N is fixed. N is a fixed number. You cannot change it. But what does change is I. So remember that I is a finite number basically, because there's a certain range of I where this inequality is true, which we restricted it to this sum right here. And if your I violates that, then that means that it's cooked for you. So basically, I can only take on the values between this monstrosity and this monstrosity. Slightly less monstrous, but still a monstrosity. So there's finite number of possibilities for n, for the values of n over b to the I. So there's a maximum. And that maximum is constant. So, therefore, remember our general term from before? AI times f of n over b to the I. This is less than or equal to a to the I multiplied by some m. Yes. This m is just a positive random number. It's just a number. And then remember, we'll take a break after we finish this guy, cause then this is gonna tear all of our brains open, including mine, because I'm tired.
How about, rather than taking a break because it's already 1 and today's the first day off, let's all go to sleep and then wake up tomorrow and do it tomorrow.
Oh my god, that's a great idea. Okay, let's continue then.
I know,
fine with
right?
that.
So remember,
We will continue.
this I is less than your upper bound of the sum, which is the floor of your log base b of n, like that. And then so, when you have an exponent like this, you can actually just apply it to both sides like that. If it's, okay, wait. Side note. This is pretty important for, like, in general in math, I guess. So, if a is greater than 1 and x is greater than y, then a to the x is greater than a to the y. Okay. So, in this case, your a is greater than 1. Why? Because, remember your... Oh god, I gotta go all the way back up. Okay. Where is it? Where's your recursive definition? There it is. Okay. So remember, we split the recursions into 8 parts, okay? So, imagine if you split it into 0 recursions. What are you doing, right? Okay? And now imagine if you split it into 1 recursion. Then, I mean, I guess it kind of works. Okay, yeah, maybe that wasn't the best example. But basically, okay, I don't know why I said that. I completely confused everybody. Okay. But, if it's equal to 1, if a is equal to 1, I mean, then a to the x is equal to 1, a to the y is equal to 1. Right? Okay, so we can just adjust this, right? By doing that, if you really wanted to. But we already have the less than equals inequality here, so it doesn't matter. So we just apply a like this to both sides. A to the to the log bn. Okay. Okay, let me extend this inequality a little bit. This is less than or equal to log bn. Because remember, the floor of something is always less than or equal to the original thing. that's just, you know, the definition. So AI is less than or equal to this guy, which is less than or equal to the same guy except without the floor. And then we can do the same trick from before, where you swap the A and the N. Like that. So, remember this is your original sum. And we basically just showed that your general term, which is this is less than, okay, so, well, your first part is this guy, less than or equal to that guy, and then your second part is less than or equal to a constant. Okay. So then, take your sum. I'm going to prepare myself this time and write it more to the left. And this goes up until log b n. Okay. So then this is, remember this is a second sum. Second sum. So this guy is less than or equal to the same guy. Oh my god, I have to write it out again. Fuck. I have to write it out again. Okay, Pn minus log Bn naught plus 1 to log B of n. Oh god. And this same thing up here. Basically. Okay, now notice that none of these things include an I, which means that this entire thing is actually independent of the sum. So, okay. Well, I mean, I guess this is assigned to finish after this part, but alright. So then, now we have to think about how many elements, how many times are we summing this value up? And we can just, and to do this, we can just look at the upper and lower bounds. So when you have, let's say you have like a sum from I equals 11 to 20 of 1. Okay, well, you have I equals 11, 12, 13, blah, 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 all the way up to 20. Oh my god, fucking. Okay, all the way up to 20. Okay, so then if you actually count how many, this is actually 10. So, in general, actually, you have the number of times sum up is actually equal to your upper bound, which is 20, minus your lower bound, which is 11, and then you add 1. So that's exactly what we're going to do here. Why did I put this here? Okay, let's move it down. Okay, so then this is equal to, I'm going brain dead. Okay, so we multiply by log base b of n here. Oh, I remember this part. This part's kind of ass. Okay. Minus log base b of n. This guy plus 1. Oh. Okay, wait. Okay, I feel like I'm not really explaining why I'm doing these steps. So remember, we're trying to find a tight asymptotic bound for this sum, basically. And the first thing that we want to do is basically just try to find an upper bound for this second sum. And we actually find out that it's like there's like a bunch of constants here, So then it's bounded above by a constant, which is really good for us actually. But we'll see that this a to the I term is not constant. Okay, anyways. So, continuing on, we get this guy. And then it's multiplied by n log base b of a times m, which is a constant and we don't care about it, right? So the only part that matters is like this. Everything that's bad matters. Oh god. Okay. So how do we simplify this? Well, remember our idea right now is to try and get an upper bound, right? So that means you always want to go for the less than or equal sign. This guy is your best friend right now, okay? So look at this term. We have a floor applied to it, so it is less than or equal to the original function, which is log base b of n. Okay, but now what about this guy? This guy is less than or equal to the original function, but there's a negative applied to it, right? But there's another useful thing for floors, where you actually have that the floor of x is greater than or equal to x minus 1. And so you can use that. You can just multiply both sides by negative, and you get like 1 minus x here. So that's exactly what we're going to do. So we replace this guy with basically this up here. So this becomes plus 1 minus this guy. And these two on the outside stay the same. Okay, and now we have some really nice cancellation going on. So this guy dies, and then you're left with the negatives cancel each other out, so you get log b and not plus 2 n log ba times m. I'm gonna put the m at the front actually because it's better. I feel like that's better. Okay, so then now remember what n naught is. This guy's a constant, right? So then that means that this guy's a constant. So that means that this guy's a constant. So then if you multiply by m, that means that this guy's a constant. So then this is basically just a constant and you don't care about it. So, in summary, your second sum is less than or equal to a constant multiplied by n to the log ba, and this kind of looks familiar to a definition that we covered earlier, right? And it turns out that this is actually true. You have that I'm gonna write this out explicitly. Also, I'm gonna delete this because I don't think.
Good night, by the way. I'm heading to sleep.
Alright, I'm almost done.
Okay, good night, Paul.
Okay, so I'm gonna write this out explicitly. I is equal to this plus 1 log base b of n of ai times this. This is actually an O of n log base b of a. So we have found an upper bound for the second sum, which is really nice. And that's basically the first half of the master theorem. The master theorem. So let's recollect what the fuck we learned. Okay, so go back up. We have from this first half that your first term is theta of n to the log base b of a, which is a tight asymptotic bound. I'll write that down here. N. Okay, so your your n to the log base b of a multiplied by t1. Tyler, what? This is an element of big theta of n to the log minus 2 of a. And then I'm going to put summary here. And then your second sum. Yeah, I'm getting used to writing this. I don't find it that suffering anymore. And this guy is in O of... Fuck, I forgot. Literally the same thing. Okay, and that is actually really good for us. Because this means... this means that it makes no difference in the runtime analysis. Because the reason why is because you know that your first term is already a tight asymptotic bound. And then adding on the fact that this guy has n to the log base b of a as an upper bound doesn't really change anything about the statement. So this guy doesn't do anything, basically, which is really nice. And that's the end of today's whatever. And I guess tomorrow we'll just pick up where we left off and do the worst part of master theorem, which is this piece right here, which is horrible to do. So yeah, that's it for today.
Oh, okay, let's go.
お疲れ様。
Oh,
My god. Holy Jesus. And I do have the recording. Let's see how long it is.